if you have in two-dimensional space this equation, x squared over a squared plus y squared over b squared equals 1, what does this draw? Ellipse. So it looks like this. Depending on how you change the a and the b down here, it will change your ellipse shape. Yeah? Two-dimensional. If you had the same thing as an ellipse except subtraction between them, you draw a hyperbola. And if you change a and b, this is how it would affect the picture. These are things you should be familiar with, at least visually familiar with. Now what we want to do is we want to blow this open to three-dimensional space, which means we're going to have three variables involved and see what the heck they look like. All right? Before computers, back when I was in school, I mean, there were computers, but they couldn't do what they could do now. What they can do now, the three-dimensional visualization of these sorts of surfaces was all done by hand, and they would use this thing called traces. And I'm going to show you one example of how to do a trace, and I'm never going to touch it again. Because if you go to Wolfram Alpha and you type in the equation, it will graph a three-dimensional surface for you. All right? So there's not like we can't do it. But I do want you to be able to look at an equation and identify what it is. Like, oh, see that equation? Sure, that's whatever. Ellipsoid. Paraboloid, whatever. So you have to, this is all about identification more than anything else. All right, so I think the one I wanted to start with, it's not in your notes, was one of the classic ones, which is x squared plus y squared plus z squared equals, let's do 1. Anybody know what that is? It's a sphere. It's a sphere. It's the shell, right? The outside of the ball, just the surface of a ball. Now, we know maybe that that's what it looks like, but let's act like we don't. It's a quadratic surface in the sense that, notice that at least one of the variables is squared. And this one, they're all squared, aren't they? You've got x, y, and z in the game here. We're in three-dimensional space. So I'm going to try and do what are called traces. So imagine that you've got this picture, right? You got it. I don't know what it looks like. Yeah, I do, right? Got this picture. What I'm going to do is I'm going to come through and I'm going to slice it. I'm going to take a slice of it. I'm going to just cut this surface across horizontally with a plane. And where I cut through, wherever it cuts and touches, I want to know what that shape is. So watch. Let z be 0. What is z equal 0 in the three-dimensional space? What is this? That's the xy plane. So what we're saying is, I'm going to come in here. I'm going to look just in the xy plane. What does this shape look like just in the xy plane? So come over here, replace z with 0. X squared plus y squared equals 1. It looks like a circle, right? Radius 1. So if I was looking from the top down, this would be x, this would be y. Z's coming out at us, right? If I'm at the xy plane, or I'm sorry, if z is 0, I'm actually on this plane. It draws a circle radius 1. Yes? Now what I'd like to do is I'd like to move up a little bit and look at another slice. So let's change z. What would happen if I change z? Let z be, let's let z be 1, okay, just to see what happens. Okay, what would we get? X squared plus y squared. Z is 1, right? So 1 squared is 1 equals 1. And what would that be? X squared plus y squared equals 0. Uh-oh. That is a circle with radius 0, which means it's a point. So if I were to look at this picture and come up 1 unit out towards us, I'm going to be at a single point. Do you all see that? No? Yes? So I'm going to have a point here. This corresponds to z equals 0, doesn't it? this point, looking from the top down, is z is 1. Now, what I'd like to do is draw it three-dimensionally over here, just so we can see it. Here's x, here's y. When we were flat on the ground, we had a circle on the ground, right? Like this. Radius 1. When I move up on the z-axis 1 unit, I have a point. So if I look straight down on that, I get this, don't I? Can I go any further than z equals 1? Can I go up any further? Out? Can I go any further? No, I cannot, right? Do y'all see why? What would happen? Let's just try z as 2. You get x squared plus y squared plus 4 equals 1. And when you moved it to the other side, x squared plus y squared equals negative 3. You can't square two numbers, add them together, and get a negative number. So there's no solution here. No way you can do it. Well, not with real numbers, right? So this isn't work. So we got to go something smaller, something between 0 and 1. Or sorry, yeah, 0 and 1. So 0.5, how about 1/2? Can I do it that way? Z is a half. So if I do a half, x squared plus y squared plus a half squared is 1/4 equals 1. Subtract from both sides, x squared plus y squared equals 3/4. And then that means the radius here would be root 3 over 2. Square root, top and bottom, right? Remember, the other side of the equation is r squared. What's root 3 over 2? Get on your calculator, go ahead. Remember, this was 1. Root 3 over 2.
Oh, it says root 3 over 2.
0.86. That's a smaller radius, isn't it, than this one? So 0.86 would be about like right here. That's what's happening when z is, what, 1/2? And I could keep doing this, couldn't I? Over and over and over. More values of z. And what I'd start to get are these like rings. And they keep getting smaller. So over here in this picture, I have a ring that's been moved up, and then another ring that's moved up, and then moved up, and then moved up. That's a terrible picture. And what happens when you put, maybe I should draw it this way first. It's the top half, like this. It's the top half so far of the ball. That's a horrible picture. I hate that. Do y'all see it or not?
I see it.
You see it? Okay. And then what we would do is we would pick some negative values for z. Like z is negative 1. Z is negative 1/2. And then what we get is all these rings going the other direction. And when we put all those rings together, you get this shape. And the shape in this case would be a sphere, right? Maybe if I start here and then just start drawing bigger rings. I don't think this is going to work either. You know, put all those together and you get this sphere. Close enough. Now, that sphere is very easy to see what's going on because we keep on getting these circles, right? I went ahead and I came through and I looked at it from the top down, right? Why not come in and look at it from the side? In other words, why don't we let x be 0 instead? If x was 0, the equation would become y squared plus z squared equals 1, wouldn't it? And that's a circle, but in what plane? The yz plane instead of the xy plane. So it's almost like you're looking at this ball, but from this side, or sorry, from this side. And what stops me from letting y be 0? Nothing. So do you see the inherent problem in this? It could take you a while to get a good idea of what it looks like. And even if you do all the math, the picture you draw still may suck, and it may be hard for you to figure out what's going on, right? So I won't ask you to do that by hand. But what I do want is for you to recognize them. So let's take a look at all the important quadratic surfaces. The first one, the first quadratic surface that we're going to look at officially is a cylinder. So what makes a cylinder? Well, it says here that all your traces, remember traces is what I just showed you? Each one of those little rings I drew was a trace. All cylinders have traces that are circles and lines. Here is a cylinder. See it? Cylinder. It's hollow inside. See the cylinder? Okay. This is the equation of that cylinder. X squared plus y squared equals c squared. I could use r. That's the equation of a circle, isn't it? In two-dimensional space, it is a circle. But in three-dimensional space, there's no z here, right, in the equation? So z is what we call free. And so what it does is it draws a bunch of circles, but since z is free, it goes up the z-axis and down the z-axis. And you get the cylinder. Make sense? Now let's look at the traces. So this is kind of cool how this traces things work. I only say it's cool because it took me freaking forever to write the program to make it do this, so it's worth us looking at. All right, so show trace curves. And where are my planes? There they are. So just imagine coming through this cylinder, all right, and cutting it with these planes. These planes are parallel to which plane? Can you tell? Those are parallel to XZ planes, right? And so this would be like holding your y value to certain constants, and every time you did that, you'd be cutting through. And notice everywhere I intersect, I'd be getting lines, wouldn't I? If I do that and it doesn't matter where I change or how I change that, as I move through different values, I get lines all the time. Now if instead I do planes that go this way, same thing's going to happen. I'm going to get lines, right? But if I cut it with the plane that's parallel to the XY plane, like this, and move that up and down, my traces are circles. Yeah? So really the definition of a cylinder is that all traces are either circles or lines. Is there anything stopping me from changing this variable, make it x squared plus z squared equals c squared, and let the y be free? How would that change the picture? Yeah, if I use x and z here equals a number squared, right? That's going to let y be free, which means that the cylinder is going to open out the y-axis. Make sense? And then what if I use y and z and not x? The cylinder will go out the x-axis, right? Like this. Still have lines and circles as traces. Questions? Cylinders, pretty simple. Next one, parabolic cylinders. These are cylinders where your traces are parabolas and lines. Here it is. Looks like a sheet of paper that's just been folded. That's all it is. The equation is z equals cx squared. That doesn't look like the right picture. Oh, no, yeah, y is free. So y goes down this way. That's right. So if you start to take slices through here, right, if I slice it this way, I get parabolas, don't I? But if I slice it that way, oh, then I get lines. You see these lines? So it just depends on how you slice it. Major thing is the equation One of your variables is missing, right? And that's the axis which that folded paper goes down. Also, only one of the variables is squared, right? Z is linear here, x is squared. And that's the way parabolas worked, right? Y is x squared. Well, z is x squared does this. Changing this value of c just opens the parabola up. And if you make it negative, it'll do what? Fold it over, right? If I make my c negative, I don't know if I actually included that in here. Flip it over. See that? So get those out of there. So it actually flips it over. All right, that's parabolic cylinders. These are the different cases, right? This was z equals cx squared. It went down the y-axis. Here z is cy squared. Notice it goes down the x-axis. And are there more? X equals cy squared would go up the z-axis. X equals cz squared would go out the y-axis. So there's all these different variations, right? What you need to be thinking is only two variables appear. One of them's linear, one of them's quadratic. How do you identify a cylinder? That's visually, but if you're looking at the equation, how do you know it's a cylinder?
Only two variables.
You have two variables, both squared, equals a number squared, right? Added together. See, we need to start to, that's the part you need to start to pick up on, is if you can just look at the equation and say, oh, I know that's a cylinder. Which means you're going to kind of have to memorize some of this stuff. Next one, an ellipsoid. Looks like an egg. All traces are ellipses. All your traces are ellipses. Now, in an effort to save time, I'm just going to show you all the traces. There's a bunch of traces. Slicing it that way. Boom. Cut it up the other way. These are traces coming like this. And then if you want to go like this, cut it this way, there's a bunch of traces. All of those are ellipses, no matter how you cut it. And look at the equation. Can you all see that down here? I know it's kind of low on the notes here. Can you all see that? This is all in your book, too. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Very much like an ellipse back in two-dimensional space. All variables appear, right? This is the first time all variables appear. They're all squared. They're all being added together. Equals 1. That's an ellipsoid. If you change A and B and C, that just changes your shape, right? Elliptic paraboloids. Traces are ellipses and parabolas. These start to get harder and harder to visualize before I show them to you. Is that what you were thinking? Ellipses and paraboloids, or ellipses and parabolas. It's basically a bowl, isn't it? It's a bowl. Cone would come to a point, right? This is curved at the bottom. Kind of like the absolute value function is a v as opposed to a parabola being curved. So this is a kind of like a bowl. And let's see. Traces, there are your traces. If I look at all those traces, what are those? Ellipses. What's that? What I'm doing is I'm taking the xy plane and I'm moving it up and I'm slicing. So that's really like changing the value of z. If I do that, I get a bunch of ellipses. If I cut it a different way, yz plane, start cutting it this way, those are all what? Parabolas if we look at them from the side. And then if we cut them the other way, we're going to get parabolas again.
Do you ever get circles if you cut them in the xy plane?
Yes, if A, B, and C are appropriate. In fact, I think you could probably, let me see. If z is a constant, right? I'm sorry. Yeah, if you hold z, right, to be a constant, and let A and B be the same thing, that's going to be a circle. Like if these numbers are the same, that'll be a circle. So if I change A and B to be the same values, went a little too far.
Drag them all the way up.
Yeah, I guess, well, I don't know how far it goes because it's a generic code that I wrote. Just copy and paste a lot of my code. But let me do the, this way. Yeah, those look like circles. Okay? Good question. That's like all ellipses. A circle is a special case of an ellipse. Right? That's all the same thing. Elliptic paraboloids. So you have ellipses and parabolas. And it's the same thing, different direction though. Look. I didn't point out the equation. I should go backwards. Look at, for this elliptic paraboloid, two of the variables are squared, right? One isn't. And it's on the other side. Notice it doesn't say like equals 1. So that's kind of a tip to you that you've got an elliptic paraboloid. Anytime you have two variables that are squared and the other variables on the other side, and there's addition over here between these, you've got this. And then you go out different directions. Okay, I went too fast. Get out of here. Okay, get out of there. Hyperbolic paraboloid. Hyperbolas and parabolas. This one's hard to see. Let me cut it with XY planes. So I'm cutting it with sheets that are parallel to the XY plane. If I look at that from the top, what are those? Hyperbolas. It's like this. That's what a hyperbola was. If I instead cut it with YZ planes, I get what? Look at it from this side. Parabolas. Right? Those are parabolas. These go down forever and keep going. If I cut it with the XZ plane, look at it from this side, I've got parabolas again. Look at the equation. Does that equation look similar to something? It's the one we just did, right? Before this, which was what? Elliptic paraboloid. The only difference is what? A minus sign. That little subtlety changes the whole thing, right?
Call this saddle shape or
Yeah, later on what we'll do is we'll actually be able to find this point here in the middle, which is called a saddle point. Saddle point looks like a saddle, right? But that's later. We'll need calculus for that. Okay, what's this? Hyperbolic paraboloid. So, oh, wait, this is the same one. Sorry, this is just different ways you could go out with it. So you could go down different axes. Okay, here you go. Here's your cone. Okay, cones. The traces are ellipses and hyperbolas and possibly lines. So there's your cone. Notice it's a point at the bottom, and it also goes out both ways. The elliptic paraboloid was a bowl, right? And it was curved at the bottom, and it did not go both directions. This is a cone, and it comes to a point and goes out the other direction. If I cut, I get what? These are ellipses, sometimes circles. If I cut this way, I get what? Hyperbolas. These are matching pairs, like here, 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 here. So I get hyperbolas. We also have lines. Lines come down the edge of the cone. Let's look at this equation. Wait a minute, I thought we saw that already. I thought we saw two variables squared, addition between them, the other variable on the other side. I thought we saw that. It's squared though. That's what makes it a cone. And then you can take all different variations of this, right? What if the variable on the other side is y instead of z? Z's over on that side. Well, then your cone goes another direction. And you keep this going. Almost done. Hyperboloid of one sheet. Looks like a nuclear power plant thing, kind of, doesn't it?
Yeah.
A little bit. we can change values. Whoa, I blew that up, sorry. Let's look at the equation. All variables appear in here. All of them are squared. 2 of them are positive. 1 of them is negative. And we have equals 1. If you took that 1 away and made it a 0, you could move that to the other side, couldn't you? And then it would no longer look like this. It would be something else.
So the negative variable would be like a 3.
No, the negative variable, actually, the only thing that's going to tell us in this picture is which axis this tube thing opens up. So notice that the negative is on the z, and notice that this opens up the z. If it would have been positive, negative, positive, then it would have gone down the y.
So like if z was 0, it'd be a ellipse. Or
If what?
If z was 0, would it be?
An ellipse, yes. You're talking about those slices right there, actually. You slice it that way, they're ellipses. And sometimes circles, if A and B are the same. And then the other slice this way, hyperbolas. But they call this a what? An elliptic hyperbola? No, hyperboloid of 1 sheet. Now the next example is a hyperboloid of 2 sheets. This is the last example. And look at the equation. Difference? 2 negatives, 1 of them positive, equals 1. And there you get 2 bowls. You get a bowl on top and a bowl on bottom. Not a cone on top, cone on bottom. Bowl on top, bowl on bottom. And what would happen if we try and move them to get closer? Let me see if I can get them to. No, it's not going to work. Well, if they ever met, then it would be something different. That's right. But that's why they call it of 2 sheets, because you separate. If it becomes 1, then it's the hyperboloid 1 sheet. So it's like, imagine them coming together, and then they turn into that nuclear power plant looking thing. All right. Of course, you can go out different directions with those bowls. I think this one will be worth us doing. I've got about 12 minutes. All right. Reduce this. So I give you an equation. This is what you have to do on your homework. And this is what you'd be expected to do on an in-class test. That is a quadratic surface. We know that because all 3 variables appear. They're all being squared, right? I only need one of them to be squared to be classified as a quadratic surface. But they're all here, they're all squared. The question is, what is it? What does this draw? Well, what did we do way back in the beginning of this class when we saw something like that? We completed the square, didn't we? Let's get things together here. X squared minus 2x minus y squared plus 2y plus z squared plus 4z. I'll go ahead and take that 2 to the other side, make it negative 2. These 2, I can complete square on that right away, can't I? Take half of negative 2, square it, add and subtract. So this becomes x squared minus 2x. I'm going to add 1 and subtract 1 right there. Yeah? What about this, though? Can I do completing the square on this? I have to get the negative out of there first. So that means I'd have to, well, let me write it. Pull the negative out, be left with y squared minus 2y. Can I complete the square on this one? The z squared plus 4z. Can I do that right now? Yes? So what am I going to add and subtract? Plus 4 minus 4? We've done this already. That's why I'm kind of not really saying a lot. Okay. These three turn into x minus 1 squared. Then I have minus 1. So that's this. I never completed the square on this one. What would it have been here? Y squared minus 2y. We did what in here? Plus 1 minus 1 again? That'd be in that parentheses. So I would have had the negative sitting out here. In parentheses, completing the square, I get y minus 1 squared minus 1. I am going through this quick because, again, this was part of a homework assignment. I did several of these in class. This should be z plus 2 squared minus 4 equals negative 2. Anybody disagree or see an error anywhere? All right, so I have x minus 1 squared. I'm going to take the minus 1 and the minus 4 to the other side, which would give me a what? Plus, so plus 3. Now I am going to have to deal with this guy too, but I want to get all that other crap out of there. Minus y minus 1 squared. This minus and this minus can become a plus there, plus 1. Plus z plus 2 squared equals 3. That's where I am now. And finally, take the 1 over, and I get, dun, 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 x minus 1 squared minus y minus 1 squared plus z plus 2 squared equals 2. If I did all the completing the square correct, that's what it should be. What the hell is that if I graph it? So you see this x minus 1, forget that it's, I'm thinking out loud here. Forget that it's x minus 1 squared and y minus 1 squared and z plus 2 squared. All that ever happened when we put a number inside here is that it moved the center of this thing around, didn't it? So like if I had a sphere, these numbers would move it, and that would give you the center of the sphere. This is some quadratic surface that we should recognize that's just been moved. All right? So instead of trying to mess with these numbers, just think about this. You've got x being squared, you've got y being squared, you've got z being squared, right? All variables appear, they're all squared. That immediately rules out some of the things, right? You also have that 2 of the variables are positive, 1 of them is negative. And you also have a number on the other side. Which of the ones we looked at looks like that? Now, in your book, there's a summary. Who has a book? Right there, okay. On page 578. There's a table that summarizes all these shapes, and it has the general basic formulas there. It's a nice reference page to go off of. Anybody have a guess or an educated guess? What do you think? Hyperboloid 1 sheet? You agree? Okay, let me go back in my notes to a hyperboloid of 1 sheet. Hyperboloid there we go. There's the equation of a hyperboloid of 1 sheet. 2 of the variables squared, subtraction on the other, and a 1 on that side. I need to see if I can make that look like that. Divide everything by 2? Okay, I'm going to go back to the end of this. here's where I was. So I'm working with this right here. Divide everything by 2. So you get x minus 1 squared over 2 minus y minus 1 squared over 2, and then plus z plus 2 squared over 2 equals 1. I do agree. This looks like a hyperboloid one sheet. Now, a hyperboloid one sheet doesn't technically have a center, but what I can say is that this thing has been shifted, right? It's shifted. So if we were to say that 0, 0, 0 was like the origin of this originally, everything's been moved. Then it's been moved to where? 1, 1, negative 2. So the whole thing went and got moved out the x-axis 1, over the y-axis 1, and down the z-axis 1, right? Which way does this thing open? Was this the nuclear power plant one? So it's this one right here. You've got your x and your z variables are squared, or positive, sorry, squared and positive. Your y is negative, 1 on the other side. It should look like that. So imagine again, like the center was in there. We moved it over the x-axis 1, over the y-axis 1, and the whole thing down the z2, right? That picture. Also, what's a for us? Square root of 2. Right? Because look at that formula. It's x squared over a squared. So we would say here, a is root 2. What's b? Root 2 again. And c is root 2. So they're all root 2. It's kind of boring, but that's what you need to be able to do on the test. I give you a general equation. You're definitely going to have to complete the square. And then you need to be able to match it up to something. Now, are we going to memorize all those? No, I don't like that idea. I don't like that idea. I'd prefer that you have a reference sheet, you know, something to go off. But we'll address that later as we get used. I'm sorry? Yeah, I'd provide it for you. It would probably be that page right out of the book. Remember, my philosophy on formula sheets is that in the real world, you're never locked in a room without access to any information, right? Only in college do we like to do that, right? So being resourceful with information to me is an important skill. So knowing to go, okay, I know where to go to get that information, right? All right, so your homework for this section, go ahead and get working on that. And we're done with 10.6. See, it's only it's only a couple of problems, right? Because I say only do odds. So just a few problems out of there. Yes? Homework is never technically due.
I meant the mini exam.
Yeah, is the mini exam due on the 8th?
It's Monday, the 8th. Yeah.
Monday, yeah. So, yeah, is that? Yeah, you have everything you need. Nobody's come for help. Don't all show up in my office Monday morning with all these questions. I would have rather have you come by before.
It's already decided.
Let me turn this off.